Hey there, School of Tomorrowites. This is actually going to end up being mostly a Python talk, but for orientation purposes, welcome back to my channel. The Wanderers are, I would say, a good translation for wanderer is flaneur. Flaneur? Flannery. I find these people who go exploring deserted malls with their camera equipment and then publishing to YouTube, they call that being a flaneur, and I think that's interesting. These were people, when the word was first coined, they were amazed by the transformations going on, brought along by industrialization in particular, and they were self styled chroniclers. They were there to bear witness. They would just stand around and watch the world change and maybe have a sketch pad or a canvas. They're observers, but it had some social it was a role you could play. The synergetic slide deck, most recent telling, would be August 19th. Excuse me. Yeah, that's right. August 19th, 2020. So last time I went through that. In case you're wondering if I've gone through it since, I have not. And Applewhites visit Oregon. 1996 is when the Applewhites came out here. I mentioned in a recent sort of autobiographical section that I last saw Applewhite in the symposium in Washington, D.C. about Bucky Fuller. All right, because he was a collaborator with Bucky Fuller on Synergetics and other projects. Okay, but what I want to do with that as a transition, I'll just show you one more thing about Ed. In my Bismo, go way back to the beginning. He lived until February 2005. So I have Ayatollah of the tetrahedron here, and he lived long enough to actually see this one. So we were still in touch around here. But let's see, when did he pass away? 2005, February 15th, and this was written February 3rd. Okay, so it's very shortly after that. So going to the Python, we have a nice clear clean namespace here. In other words, I've just restarted the kernel. So this is like the bare minimum that you're going to have. If you're not familiar with Python, what you're looking at on the right is an interactive namespace where I can mention things that Python knows, like give it names. I can use Python names. Like one of those is dir, but where is that? I don't see it listed, because to be consistent, what I'm trying to tell you is the only things I can get away with typing and having Python understand is got to be on that list. Well, the answer there is inside a built-in, or built-in's a synonym. You've got inside of there a much larger vocabulary that we take for granted and that we want Python to kind of hide from you, because it's sort of the what you get when you boot up brain of Python. A lot of it is errors and warnings, things that can go wrong. It's kind of the rubber of the rubber room. When you bump against something, like it makes sense when you go into a container, think of Python as a namespace, that you can also bump up against stuff. And so that would trigger like an exception of some kind. So it's still that nice clear namespace. Just because I checked inside of built-ins didn't change anything. That's all that's there. What we're going to do here now is use your imagination as I just show you some source code. Think about, for example, the 12 CCP spokes. That's where you've got like a basketball surrounded by 12 basketballs, You could say 6 in the same plane, 3 above, 3 below is one way to look at it. And how those are all oriented with respect to each other. You've got some choices already. The CCP is a well-defined cube octahedral packing from the center outward, 0 or 1 sphere, and then 12 around it, and then 42 in the next layer, 92 in the next, 162. We're building the CCP matrix, you could call it. If you disappear all the spheres, leaving only the rods between adjacent centers, you get what's called the IVM. And our goal here is to wander in the IVM, to sort of start at 0, 0, 0, 0, and for 1,000 iterations, pick one of 12 directions to sort of hop forward. And we've done this in a previous video, and we've introduced higher power than floating point numbers. In other words, to keep track of our position. Now, because we're using something called quadray coordinates, actually our position will always be measured in integers. All the sphere centers have whole number addresses in this, actually positive number whole number addresses, 4 tuples, with respect to the 4 basis vectors of the quadray coordinate system. But once we start getting into lengths between 4 points, those are going to be, right, we're going to use Pythagorean theorem, distance formula kind of stuff, second roots, and so on. So it's going to pay off to have precision to 1,000 bits. Now those are bits and not digits. So what we're going to do is go ahead and run this and see how it opens up our namespace. And take special advantage of that A, B, C, D will now be defined as 4 random vertices. Okay, and what this script then goes on to do is compute the 6 links between those 4 vertices, feed them to an older tetrahedron that can only compute volume, and spit back the volume in terms of tetrahedral volumes. This is the Bucky Fuller way of doing volume in synergetic geometry. But we haven't run this code yet, right? So just to confirm, our namespace is still tiny. And it doesn't actually define tetrahedron. It defines tv.tetrahedron. So, it brings it in as a module called TV, which is off here to the side, TV for tetravolumes. So there's quite a few modules in play here. The point being, our current interactive environment is still very clean. And when I run this rantet here, which I'm going to do by hitting the green arrow, it's going to give me actually the volume of the tetrahedron ABCD it just generated in tetravolumes, but it's also giving me back the 4 corners of that tetrahedron, A, B, C, D. I got them out of order there, but it doesn't matter what the order is. It's just 4 points in space expressed as IVM vectors or quadrays here. And these are integers, but to 1,000 bits of precision. And the fun part now is this new tetrahedron. It's a little more, I could say, sophisticated, in that the way you initialize it is not with 6 lengths, which is how we were doing with the TV.tetrahedron. This tetrahedron wants the 4 vertices expressed as vectors, right, from the origin 2, A, B, C, and D. We'll just store those upon entry, upon initialization. Just onboard those, take those in, save them in self. But now, whenever we ask about a length, we'll get it returned immediately. We can ask without calling a function. So-called property decorator here is going to let us refer to the lengths just by going like .ad, .cd, and get back the links. Same with volume. So let's take advantage of the fact that we can get this tetrahedron simply by running the code. Hit the green arrow. Now there is, in our namespace currently, a TV tetrahedron, which is the old one, and it wants us to give it lengths. That's available to us. But now, because of what we just did, we also have, at the very top level, tetrahedron in main, because we just ran this, and it's therefore now like directly available. The same way A, B, C, D are still available. They haven't gone anywhere. We just keep kind of, as we run more modules on the left, you could say we pollute our namespace, and we can quickly get it like too busy, like a chalkboard where no one could follow anymore. But I don't think we're there yet. We've just got 4 vertices that we're paying attention to. They're somewhat randomly generated. And now we're going to create a tetrahedron of the new kind by passing in A, B, C, D. Simple enough, right? And to get that volume, oops, typed it wrong, T dot volume, all we have to do is like that. We don't have to call anything. And there's the same integer whole number volume. So to run through that quickly again, every time I hit the green arrow on rand tet, I get a different ABCD, which I can then use to generate a tetrahedron and then get its volume, right? And this has a tiny little bit of noise in it, because even out to 1,000 bits of precision, you're going to have some tailings. But you're seeing how we are showing how any randomly generated tetrahedron in the CCP, if you just randomly walk from the origin to 4 different vertices and connect those 12 or 6 edges, connect those 4 vertices with the 6 edges, the volume you have thereby embraced is a whole number volume in terms of tetravolumes. And our fun here is to recast the tetrahedron slightly differently. So instead of taking lengths, it takes just the vertices and computes the lengths internally when we ask for them. So let's do that. I haven't actually shown that too much. What's AD right now? Okay, so that's crazy length like that. What's BC? Okay, so we know these are all going to be legal tetrahedron because of how we've generated them, right? We're just connecting up, we're not passing in lengths, which can be impossible. We're passing in vertices. The volume, is this the last thing I'll mention, is quite interesting in that the method is defining other functions internally, the sort of subfunctions you need per Gerald de Jong's volume formula is broken out into the same 3 chunks that we were using previously, but as top-level functions within the class. So I'd say I kind of like this design a little bit better. We indent under the volume function these sort of subfunctions and call them inside of the volume function with a shared namespace of all the links to the second power. We have to dig those out of dunder dict, if you know about Python, where it stores its instance values. Pull out the 6 edge links, square them all, or second power them all. Get these A2, B2, so forth. Those are temporary variables, but they are also shared access, so that these functions underneath, indented, have shared access to those constants. We treat them as constants. And then finally, a very simple, easy volume expression. No constant here, just divide by 2 and take the second root, and that's the volume. Then we also have the XYZ volume involving the synergetics constant, right? So if I want to go T's volume, I'm going to get a whole number, but if I go back to XYZ volume, of course that won't be usually, right? Okay, so Python at its finest, combination of pre-scripted code and sort of a calculator look and feel on the right side. Your focus is more the mathematics, the thought pattern is right brain, you're thinking polyhedron stuff. And yet you're also programming. And this is not something you could really do that much on a calculator. So I often am still in this day and age, in 2020, not contrasting Python with a competing language like F#, but with the whole curriculum based on calculators, based on you don't have a personal workspace, you don't have room to share files, you don't have a GPU, and the social inequities if you do, the privileges you have if you do, and that we don't talk about that as part of education reform. Like if you want a hope of being in this curriculum, um, you need to be provided with, and babies are helpless. You don't just expect a baby to go out and get a job. I'm not saying you're babies or anything. I'm just saying if you have a university system worth anything, you're going to offer facilities so that people can work out, right? Do gym work, right? It's not like until you're strong, you can't come in the gym. What? Doesn't make sense, does it? All right. Talk more about edu policy at some other time. Talk to you soon.